Bernardos and Stanislaw Wazowski patented the first electric arc welding method using carbon electrodes in 1885. In 1888, Nikola Garvalich used consumable electrodes to arc weld for the first time. Jumping ahead a little bit, in 1904, Oskar Kelgenberg invented the first coated electrodes which vastly improved the quality of welds and stability. By the 1930s, SMA weld grew more popular at construction sites and shipyards. This was largely due to stud welding. In 1927, the development of an extrusion process reduced the coating electrodes while allowing manufacturers to produce more complex coating mixtures designed for specific applications in the 1950s. Manufacturers introduced iron powder into the flux coating, making it possible to increase the welding speed.
Hi, have you ever wondered what the numbers on an electrode means? Well, thanks to the electrode classification numbering system, we can find that out. For example, the E in a 6010 rod stands for arc welding electrode. The 60 is the tensile strength, the 1 is the welding position, and the 0 is the flux composition. All of these are very important when considering the welding job you're trying to do, and different rods are used for different jobs.
To explain the coating elements and their function on shielded metal arc welding. So to begin, cellulose is basically the shield. It protects it from contaminants in the atmosphere, which will lead to poor quality and lead to dysfunction within the weld. And then we move on to iron powder. That increases the deposition rate and the efficiency in the welding process. Mineral functions, mineral fluxes, stabilize and equal better and more improved quality of the weld, leading to lack of porosity and leading to lack of undercut and cold lap. Basically, all of these qualities lead to a crucial role in ensuring a strong, clean, and high-quality weld by providing shielding, high quality and increased deposition rate, arc quality, more stabilized and more improved quality. All of these equal contamination, deposit rate, and arc stabilization equal a good weld quality.
Fast freeze electrodes deposit a weld that solidifies or freezes rapidly. E6010 and E6011 are examples of this. Fast fill deposits metal rapidly. E7018, E6024, and E6027 are also examples of this. Fill freeze characteristics between fast freeze and fast fill. E6012, E6013, and E6014. And low hydrogen designed for medium carbon and alloy steels. 8 represents low hydrogen rods.
The core metal in welding rods refer to the metallic materials that forms from the rod's core, which melts during the welding process to act as filler material. Mild steel welding rods, the core is typically low carbon steel used for carbon and mild steel. Stainless steel rods contain stainless steel alloys for corrosion-resistant applications. Aluminum rods made for lightweight, non-corrosive welds. The core metal directly affects the weld's strength, ductility, and resistance to corrosion of wear, making it a critical factor in selecting for the appropriate job.
Hi, I'm going to show you how to weld with 5 different welding rods and the pros and cons of each. We have 6010, 6011, 6013, 7018, and 9018. Now right here is where I use the 6010 electrode. You can see it had deep penetration, fast freezing, good for strong welds, not good for beginners, and a lot of slag gets trapped underneath sometimes, but with also a lot of spatter going everywhere. Right here we have a 6011 electrode, good for tacking, suitable for welding dirty or rusted metal, and good for filling gaps. But it's very difficult for beginners. Some inverters won't run them. See there? Right here we have a 6013. It was suitable for AC or DC arc. It was easy to maintain, It's a clean, low bead, but produces a lot of slag and is not suitable for rusted, dirty metal, and has a low penetration. Right here, I use a 7018, a strong, smooth surface, versatile. It can be challenging to control at first, but once you get the hang of it, even though it produces a lot of slag, you just gotta chip it off. And right here, we have a 9018. Big, strong, it can hold, but it's really hard to use sometimes. Slag gets a lot more trapped in it.
It's a welding rod oven, an electrode oven, or an electrode stabilization oven. These ovens come in many different sizes, but they all do the same thing. They maintain the welding electrodes at a controlled temperature from 225 to 300. This is so that there's no moisture from the air that can get into the electrode. A moisture absorption from the air can cause defects in their welds at the end, like porosity and cracking. The oven is especially important for electrodes that are low hydrogen, like 7010 and 7024. The 6010 does not need to be kept in the oven. It is what's called a cellulosic coating on there, and that is where they have organic material in the flux, and that organic material makes it so the moisture absorption is a lot less than your other rods. After the electrode has been out of the oven and in the air with moisture for up to even just an hour, especially in Florida where it's humid, the electrode's going to have to go back in the oven for about 4 hours and bake in there before it's usable again. The temperature gauge is on the back. The temperature gauge on the back of the oven. There's Fahrenheit and Celsius, and there's this little arrow here, and you just want to turn it to the temperature that you are choosing. Right now we have it set at 250 because we have our 7010s and 7018s in the oven. Alright, so here we've got an electrode, a 7018 electrode that's been in the oven, fresh out of the oven, how you're supposed to have them. And this one is fresh out of the dumpster. Who knows how long it's been in there, so it's definitely got moisture. We're going to show you the difference between the two. This is the electrode that we used that was from the oven. You can see that it's consistent and there's no porosity here. With this one, the electrode melted at different speeds, and there are points of porosity